Welcome to the Coherent Laser Safety Training video. Before we begin, please note the copyright laws that govern this program. If you wish to pause this video, you may do so at any time. This video presentation will discuss hazards and control measures associated with various lasers produced by Coherent. Hazards in the lab fall mainly into two categories: laser beam hazards and associated eye and skin hazards, and non-beam hazards, which include chemical, biological, and electrical types. Additionally, other types of non-beam hazards, such as fire, asphyxiation, and mechanical and their respective control measures, will be discussed.
This video is not intended to replace information and training given to employees in their local language.
Hi, I'm Luke.
And I'm Akari.
Believe it or not, we're
Self-aware particles of light.
here today to talk to you about laser safety.
Why are we doing that?
Our viewers have signed up for a class at Coherent, and we want to make sure that they are perfectly safe in our lab.
That's a great idea. Lasers, especially Class 3 and Class 4, can be dangerous. But how would we know they really know their safety rules?
Well, the viewers have to take a quiz at the end of our video and get 70% or better to pass.
What happens if they fail?
Well, they can't fail. They can watch this video and take the exam repeatedly until they pass.
Phew, that's encouraging. Let's get started.
Okay, but before we talk about anything, we need to talk about common laser safety terminology.
Like what?
MPE, OD, and NHZ.
MPE, OD, and NHZ? I know what they are.
Okay, why don't you explain?
When we speak of safely viewing a laser beam, it is in terms of MPE, or maximum permissible exposure. This value represents the highest dose expressed in amount and duration of laser radiation to which a person may be exposed, without hazardous effects or adverse biological changes to or within the eye or skin.
Well, that's great. What about OD?
In discussing laser safety eyewear, an important characteristic is its optical density, or OD. Typically, this numeric value is marked on the lens or frame and represents the attenuation factor of the filter to the base of 10. OD2 attenuates the beam by 10 to the second, or 100. OD3 attenuates the beam by 10 to the third, or 1,000. OD4 is 10,000, and so on.
Why don't we give them an example question?
Okay, so we have a CO2 laser here lasing at 10,600 nanometers and 1,000 watts. Now look at this pair of glasses.
It says OD3 at 532.
Will this protect our eyes? No. Did I get anyone?
I don't think so. Good job, viewers. But let's break it down for the people you may have gotten.
Great idea. So first of all, the wavelength numbers don't match. The eyewear is clearly marked for 532 nanometers. The CO2 laser is lasing at 10,600 nanometers.
That should be a dead giveaway.
But just for the sake of argument, let's say it was lasing at 532 nanometers.
Well, it can't.
I know that, but just imagine a 532 nanometer at 1,000 watts.
Will that eyewear with OD3 at 532 protect you?
I see where you're going. The answer is still no.
Let's do the math.
The eyewear still couldn't protect you because even with an OD of 3,
the power of the laser will only be attenuated to 1 watt. Class 2 lasers, which are considered safe, are limited to visible beams less than 1 milliwatts in the CW. And it's only considered safe because a human blink reflex will limit the exposure to 0.25 seconds. In short, the attenuated power at 1 watt is 1,000 times greater than what is considered minimally safe.
Let's put it to the test.
Oh, that's a burned eye for sure.
Well put. Akari, tell us about NHZ.
NHZ stands for Nominal Hazard Zone. It refers to the distance within which the level of direct, reflected, or scattered radiation during normal operation exceeds the applicable maximum permissible exposure. In basic terms, the NHZ distance represents how far away you must be from the laser without protection. With low-power lasers, This distance is usually quite small. High-power lasers, on the other hand, can exhibit an NHZ of several hundred meters.
Well done, Akari.
What do we talk about now?
Compliance. We need to tell them about all the standards that coherent lasers comply to.
The American National Standard Institute, or ANSI, and the Occupational Safety and Health Administration, or OSHA, govern the safety guidelines for lasers, such as laser classification.
To address other safety concerns, the lasers must also adhere to the Code of Federal Regulations, or CFR, CDRH, CE, CSA, IEC, TUV, and UL guidelines.
You can see evidence of coherence dedication to those standards in our laser systems, labs, and manuals.
What do you mean by that?
Well, to make sure that anyone can understand the potential hazards of the lasers in labs, Coherent has adopted universal symbols for danger, warning, caution, and notice.
Oh, those silly stickers?
They aren't silly. They can prevent a person from getting killed or injured.
I never thought of it that way. Let's explain a little more.
Okay, so the first one here is danger. When you see this label, it means that it will cause death or injury.
A warning label means it can cause death or injury.
A caution label means it may cause death or injury.
And finally, note or notice label means possible damage to the equipment.
So those are the 4 common labels you'll see at Coherent and on any Coherent products and manuals. Some systems have other warning signs like toxic gas for excimer. To ensure that you understand all the potential hazards on your particular system, refer to the safety section of the operator's manual that's shipped with your system.
Can I talk about the next topic?
What's that, Luke?
Light.
Not fair. I wanna...
Light, as we experience it in daily life, is comprised of many different wavelengths. Laser light is different in that its critical characteristic is that it radiates at specific wavelengths. Most lasers operate in the ultraviolet, visible, or infrared spectrums. Ultraviolet, or UV light, consists of wavelengths between 100 and 400 nanometers. The next wavelength group is the visible, which consists of wavelengths in the region of 380 to 780 nanometers. After the visible, infrared wavelengths are found in the range of 780 nanometers to 1 millimeter.
This means that you don't necessarily see the beam that hits you.
You may notice that there is a slight overlap in the stated ranges. This is due to the differences in each individual's ability to detect the various wavelengths.
Can I talk about the laser classification now?
Nope, still my turn.
But...
You may have heard us use the term class when talking about lasers, as in class 3 and 4 lasers. There are many types of lasers, and all of them fall into the classification system.
Which classification system are we using, CFR or IEC?
Both. CFR standards overlap with IEC, so I'll just point out where they are different as I explain.
Can I do the IEC ones?
Fine. The lowest class, Class 1, represents no hazard. Class 1 products represent no hazard during normal use. This class contains devices such as laser printers and compact disk drives.
Class 1M laser is safe for all conditions of use except when passed through a magnifying optics, such as microscopes and telescopes. Class 1M lasers produce large diameter beams or beams that are divergent.
The next class, Class 2, represents visible lasers up to 1 milliwatt of output power. Momentary viewing of this beam is typically not considered hazardous, since the upper radiant power limit on this type of device is less than the maximum permissible exposure, or MPE, of less than 1/4 second. Intentional extended viewing, however, is considered hazardous.
A Class 2M laser is safe because of the blink reflex if not viewed through optical instruments. As with Class 1M, this applies to laser beams with a large diameter or large divergence for which the amount of light passing through the pupil cannot exceed the limits for Class 2.
Class 3A represents visible lasers with a power range of 1 to 5 milliwatts and can only be safely viewed momentarily. This category includes high-power laser pointers, which should never be directed at a person's face for obvious reasons. Laser Class 3B contains lasers that have a power range of 5 to 500 milliwatts and pose a hazard from direct and specular reflections.
And then there's 3R and 3B. A Class 3R laser is considered safe if handled carefully with restricted beam viewing. With a Class 3R laser, the MPE can be exceeded but with a low risk of injury. Visible continuous lasers in Class 3R are limited to 5 milliwatts. For other wavelengths and for pulse lasers, other limits apply. A Class 3B laser is hazardous if the eye is exposed directly, but diffuse reflections from the matte surfaces are not harmful. The AEL, or the accessible emission limit, for continuous lasers in the wavelength range from 315 nanometers to far infrared is 0.5 watts. For pulse lasers between 400 and 700 nanometers, the limit is 30 millijoules. Other limits apply to other wavelengths and to ultra-short pulse lasers. Protective eyewear is typically required where direct viewing of the Class 3B laser beam may occur. Class 3B lasers must be equipped with a key switch and a safety interlock. Class 3B lasers are used inside CD and DVD writers, although the writer unit itself is Class 1 because the laser light cannot leave the unit.
Class 4 lasers are of the highest hazard level. Instantaneous and permanent damage can result from direct exposure, as well as from specular or diffuse reflections. You should be aware that Class 4 lasers are the most commonly used lasers in the training lab at Coherent. Pew pew pew!
You know laser beams don't make sounds.
Yeah, but it would be cool if they did.
I'd like to add one more thing about classification before we move on to the next topic. Any laser product can be classified as Class 1 if engineering control measures are utilized. So, for example, the Meta 10C that can easily slice through stainless steel is classified as Class 1 because a laser head is encased inside a system that will shut down if the top cover is removed. Remember, if you open the cover of an enclosed Class 1 system when the interlocks are defeated, it is no longer a Class 1 system. It becomes a Class 4.
Hey, did you hear that?
What?
I think I hear 3 blind mice.
On a serious video like this?
Well, this is a perfect time to talk about eye protection. With any laser, the greatest safety concern is with eye protection because a laser beam can be many thousand times brighter than the sun. Laser exposure to the eye of only a fraction of a second can cause permanent eye damage, including blindness.
The 3 areas of the eye that are most susceptible to laser damage are the cornea, the lens, and the retina. The cornea is a transparent tissue layer covering the front of the eye. Damage to the outer surface of the cornea may be uncomfortable and painful, but will usually heal. Deeper layer corneal damage, however, can be permanent. The lens focuses light to form images on the retina. With age, the lens usually becomes cloudy and can eventually progress to opaqueness. This condition is known as a cataract. The retina is the inner lining on the back of the eye that contains photosensitive elements. A part of the retina that provides central vision is called the macula. The small depression in the center of the macula is the fovea, which provides high-resolution detailed vision. The fovea receives most of the image from the lens and gives the sharpest vision.
Different wavelengths damage different parts of the eye. Wavelengths in the mid or far IR, as well as the mid-UV, affect the cornea. Near UV wavelengths that fall in the range of 315 to 390 nanometers will damage the lens. The most dangerous wavelengths to the eye are the ones that are focused onto the retina. This range is called the ocular region and includes both the visible and near-infrared range, which is 400 to 1400 nanometers. The cornea and the lens have a focusing capability of 100,000 times, so it's easy to understand why even a low-power beam can produce catastrophic damage to the eye.
I'd like to highlight one common misconception here. Many people believe that bright light does the most damage to the eye, but this is simply not true. As you can see from this graph, the green light is perceived to be the brightest. However, when looking at the faint appearance of light with a wavelength of 800 nanometers, you only perceive 1 to 2% of the actual beam.
Higher power laser beams exist at even longer and shorter wavelengths and can be invisible altogether.
Like I said, you don't necessarily see the beam that hits or blinds you.
The misperception of output power from a laser is one of the most reported causes of eye injury because your eye's blinking reflex to bright light only occurs for a narrow range of the spectrum. To illustrate this hazard, the first color graph represents a uniform intensity of the visible light spectrum. Now compare this to what your eye actually perceives. As you can see, both ends of the spectrum fade away, even though the actual intensity remains constant.
And now for my favorite topic.
Oh, what's that? You like to talk about something other than light?
Yes, laser lab fashion.
All yours.
So, first of all, you can't just wear any safety glasses. They have to match the laser beam.
So if there's a green beam coming out, you wear the ones with the green lenses?
No.
Fashion smashing.
No, seriously, there's a science to this.
Oh, let's hear it.
Most importantly, the eyewear must be suited to the wavelength and be able to handle the intensity of the laser. ANSI and EN standards require that all laser protective eyewear shall clearly be labeled with appropriate designation for which protection is afforded.
What's the difference between ANSI and EN standards, and what are the designations?
Good question. ANSI is American standards, whereas EN are European standards. The standards do overlap, but European standards include specifications for direct hits with the lasers, as well as specifications for alignment eyewear. Please be aware that EN designations apply to eyewear sold in Europe. Both standards require that the laser safety eyewear is marked with wavelengths and the OD, which is attenuation factor for the specified wavelengths. The OD parameter listed on the eyewear represents the degree of protection from scattered or reflected laser beams. Depending upon the OD value, a laser beam can be partially blocked, allowing the wearer to see the beam as shown with this demonstration. On the other hand, if the OD is high enough, the eyewear can completely block the laser beam. However, by using such a high optical density, you run the risk of not knowing where the beam is and inadvertently crossing its path.
No, it's a double-edged sword.
Indeed it is. So here's where EN 208 designations come in handy. EN 208 provides standards for alignment eyewear. The eyewear is marked with an R value that starts at R1 and goes up to R5. The appropriate R value for your laser is found differently depending on whether your laser is CW or pulsed. For CW, take the average power of the laser and find where it falls on this chart. For pulse lasers, take the energy per pulse and multiply by the correction factor of n to the 1/4, where n is the number of pulses in 10 seconds. Then use the same chart to find your appropriate R value. The R value provides balance between OD and visibility, protects against the beam in case of accidental exposure to the eye, allows the wearer to see the spot from the beam, and reduces the power of laser beam to below Class 2 limit. However, it is not designed for intentional direct viewing of the beam.
Well, who would intentionally look directly into the beam?
You'd be surprised, but EN 207 addresses that too. Okay, not really. You should never intentionally look directly into the beam. However, in the case of accidental exposure, EN 207 just might save your sight. The EN 207 mandates that the laser safety eyewear must maintain the indicated amount of protection during a direct hit for 5 seconds or 50 pulses at the specified wavelength and power. The EN 207 specifies 4 laser working modes: D, I, R, and M, and an LB factor scale for eyewear that ranges from LB1 to LB10.
You might want to explain what those letters and numbers are.
Right. So for the working modes, D stands for CW, I for pulse mode, R for giant pulse mode, and M for mode locked. The LB factor indicates the lower limit of the optical density. So LB3 means the OD is greater than 3, or transmittance is less than 10 to the negative third. You'll need these 2 charts to figure out if you have the appropriate eyewear for the task.
Why don't we give them an example?
Sure. We have a laser that operates at 1064 nanometers and has a pulse duration of 10 nanoseconds with a power density of 1000 joules per meter square. Will an eyewear marked DIR 1064 LB5 protect you?
That's so mean, making them work.
You suggested it. You walked them through it.
Okay. First, notice the pulse duration of the laser. According to the laser working mode chart, it falls into the giant pulse mode category, so it gets an R. Next, the wavelength of the laser indicates that we need to use the formula in the middle of the chart. This gives you an upper limit of 5 times 10 to the second joules per meter squared. Since the laser will be operating at 10 to the third joules per meter squared, the eyewear is not suitable for use.
Good job. But let's say you had to find the eyewear yourself, just given the specs of the laser. How would you do it?
Easy. You take the equation on the right side of the column and enter your power density. You get 5.30, but you can't get eyewear rated at 5.30, so you must go to the higher OD number. So you would pick DIR 1064
LB6.
Never round down. Most of us only have 2 eyes.
Excellent. Now that we've got the difficult things figured out, make sure the laser safety eyewear fits properly, providing total front and side protection.
What if it doesn't fit?
Ask your facility safety officer or instructor for a different one. Also, if you notice a scratch or a dig in the surface of your eyewear, don't hesitate to ask for a different pair.
So how do you know what wavelength you're working with?
A laser from any self-respecting laser company, such as Coherent, puts a label on the laser head indicating all possible wavelengths and maximum power at each wavelength the laser is capable of producing.
Well, that's convenient.
Sure is. Oh, and let's not forget to talk about bling.
What?
Bling, like rings, earrings, necklaces, watches, jewelry.
That doesn't make any sense. You know you can't wear jewelry in the lab. That's dangerous.
That's exactly my point. Jewelry is a definite fashion faux pas in the laser lab. It can reflect visible and invisible beams and scatter them in unintended areas and can cause eye or skin injury or even set the place on fire. Oh, one more important topic.
Let me guess. Shoes.
You are absolutely right. Coherent headquarters is located in sunny California, and it might be tempting to come in flip-flops or open-toed shoes, but those are strictly forbidden in the lab. There are plenty of heavy tools, sharp gadgets, and toxic chemicals that could accidentally land on your feet.
So protect your feet by wearing comfortable shoes that completely cover your feet.
Right. Save your feet so you can actually enjoy the beach after class.
Hey, Luke.
What?
Nice sunburn.
Yeah, I was surfing the gnarly waves on the Avia 355-10. It was totally rad, do that.
Did you stand in the path of the beam again?
Yes. I like to live dangerously. Viewers, please don't do this at home or in the lab. The main concerns for skin damage are the beam's penetration, exposure limits, and the size of the exposed area. To protect yourself, it is best to avoid moving to the beam's path at all times. As demonstrated on this pickle, depending on the strength and size of the beam, injuries can range from a slight burning sensation to actual vaporization of skin tissue. Different wavelengths of laser light affect different layers of skin. Some lasers actually pass through the outer layers to damage the underlying tissue.
Like laser hair removal.
Right. The following graph illustrates the ability of various wavelengths to penetrate different layers of skin. Keep in mind that the beam of any laser can burn through all skin layers if the intensity is high enough. That brings us into the next topic, chemical and asphyxiation hazards.
That's some smelly entry. Unfortunately, this sound studio does not have a ventilation system.
This would be a serious problem for certain laser facilities. Reactions induced by lasers can cause hazardous particulate and gaseous byproducts. An example of this occurs in material processing, such as laser welding, cutting, and drilling from a high-power CO2 laser like a Coherent diamond laser. The vaporized material can create potentially hazardous fumes and vapors that can lead to asphyxiation if in a closed environment. General ventilation safety procedures must be followed when the lasers are used in this manner. For more information regarding toxicity of particulates and gaseous byproducts, consult the Safety Data Sheets, or SDS, for threshold limit value, or TLV, of the material you are working with.
Chemical hazards can even exist within the laser itself. The Excimer uses toxic gases for its lasing medium. There are other hazardous chemicals to be aware of that are found around the lasers as well. Chemicals such as acetone and methanol, which are often used for cleaning optics, are skin and eye hazards. Therefore, appropriate precautions and protective eyewear and clothing must be used when handling, storing, and disposing these chemicals.
The laser doesn't necessarily need to be on for you to be exposed to hazardous material. Dust that is settled in the system from a process can also be hazardous. It's important to know what was processed in the system before cleaning it. Oh hey, there's a burning pickle.
Oh my god, put it out!
Okay.
The most common fire hazards are created by using improper beam enclosures that melt or catch fire, electrical circuits shorting out, and the ignition of gases from the laser process. To minimize these risks, make sure that you are using properly rated equipment and inspect for damage regularly. As you have just witnessed, it is also very important to have a fire extinguishing device near the laser equipment. Whether a fixed or handheld device, be sure that it has the correct rating and is properly sized to do the task at hand. Shh. Did you hear that?
What?
It sounded like something being crushed. It came from over there.
Oh, gross.
What a mess. How did it get here?
I don't know. I thought we burned it in the last demo.
Well, it's a good thing it was just a pickle. See this label here? If you ignore it, that could have easily been your foot or your hand. When you see a label that looks like this, please take it seriously.
That's right. Find someone else to help you do a two-person lift, or use the proper lifting devices and always lift safely. While we're on the subject of crushed body parts, let's also talk about mechanical hazards. Some of our lasers are built inside machinery that have rapidly moving parts or gases under high pressure which pose mechanical hazards. Normally, engineering control measures, like the safety interlocks, protect operators from these hazards. However, at certain times during training, interlocks are often defeated, which leaves you exposed to potential mechanical hazards. Look for warning labels inside the machines, or better yet, ask your instructor where these hazards may be, and be careful. While the laser beam can burn or blind you, the electricity that is present can kill you. So let's talk about electrical safety. First, let's look at these. CE mark and UL mark in the US guarantees electrical safety during intended dedicated use as long as internal components are not accessed. So don't use the system for anything else but what it's intended for, and don't open the electrical components unless it's part of your training. And then there's water. It's really common sense that water and electricity don't mix, but it's inevitable with most high-powered lasers.
This is because lasers, in general, are very inefficient at generating laser power and must consume large amounts of electricity to produce a beam of light. For example, high-power lasers, like the Coherent Saber motor FRED, use three-phase line power at lethal voltage potentials.
Add to that the necessity for the laser medium to be cooled continuously to keep the laser from overheating. Water is the most plentiful cooling agent, so if there is a water leakage anywhere near the laser system,
It's the perfect storm.
right. So if there's any water leakage inside the cavity or near the laser or power supply, turn off the electricity immediately by pressing the emergency stop button.
Now let's watch this demo. Humans, like pickles, are composed mostly of water with some salinity. If this is what electrocution looks like on a pickle, we don't want to see it happen to you.
Okay, I guess avoiding those hazards is easy enough if I'm already in the lab and I set up the lasers. But what if someone walks into the lab unaware that the lasers are running?
Never fear, the administrative controls are here.
What?
In any work environment that incorporates laser technology, various administrative control measures must be employed to conform to safety regulations. In addition to assuring the availability of protective eyewear, administrative control measures such as installing signs with warning lights over access doors that contain laser workstations will be required. In addition, you will notice that all training labs at Coherent have posted standard operating procedures that govern safe lab conduct. All individuals working in these areas are required to learn and abide by these rules.
Can we see some examples?
Sure, see that sign on the door? That means there's a laser system behind those doors. That light on top of the door also tells you if a laser is being operated.
Those windows are nifty looking.
They aren't just nifty looking. Like the special safety glasses with the OD coating, those windows have the same properties so people walking outside the lab don't accidentally get hit with laser beams.
Wow, but what if someone can't read or doesn't recognize the symbols?
There are even safety measures for aliens and people like that.
Really?
Yep, it's called engineering control measures. It means automated safety features are engineered into the design of the lasers.
Like what?
Many Coherent laser product lines incorporate an external interlock switch that, when connected to a door switch, is designed to extinguish the laser beam when the room door is opened. The nifty windows we mentioned earlier that prevent exposure to passersby are another type of engineering control measure. Coherent strongly recommends using engineering control measures whenever possible.
Coherent really takes safety seriously.
We sure do.
Accidents are so scary. Do you think that our video will prevent accidents from ever happening?
Unfortunately, we can never say never. Accidents can happen even to the seasoned professional. That's why they're called accidents.
What can we do to make sure that our viewers are extra safe?
How about some parting tips?
Is it time to say goodbye already? But we just met. Parting is always so difficult, but okay. Tip number 1. When entering a room or lab with a laser, never assume the laser is off, even if the laser warning light is off. Knock on the door loudly, or ring the doorbell if there is one, and wait for someone to let you in. If no one answers, put on the appropriate laser safety eyewear before entering.
Tip number 2. Never assume that a door sign and laser warning light will deter other people from opening the door. If possible, put in place entryway controls such as card readers or passcode locks, and always notify others in the area if you will be working with an exposed beam. If possible, prevent others from moving into the beam path by blocking access with appropriate barriers such as warning tape.
And last but not least, tip 3. Be sure to minimize the beam path and always use proper beam blocking devices. Be sure to remove any unnecessary equipment and power cords from the area and make sure you have sufficient lighting. Well, I guess that's it. Goodbyes are so hard. You finish for me.
Okay. The intention of this video was to give you a basic understanding of how to create and maintain a safe laser environment. For additional information on laser safety and the terminology used, you may wish to refer to the following publications and websites. This concludes the laser safety training video. You should now have a general understanding of laser safety and the proper precautions to maintain a safe laser work environment. If you are viewing this video at Coherent and have questions or difficulties, contact your instructor that presented this video. Otherwise, contact the Coherent Product Support Hotline. Now that you've had a chance to view this video, you're ready to take the quiz. If not, please hit the button to watch the video again. Remember, you must correctly answer 70% of the questions in order to receive a successful completion certificate for laser safety training. The certificate is required prior to attending any Coherent training class. For those students that plan on attending more than one laser training course, please note that the certificate is only valid for 1 year. Thank you for watching our safety video. We hope it was informative. If you felt we missed any laser safety topics, please let us know. We'll be sure to add it to our sequel. We can be reached at laser.training@coherent.com.
Good luck, and we hope to see you at training. I like marzipan and green tea Kit Kats.
You take bribes?
Shh. Oh, Mike's still on?